Write the integers from 1 to 10 around a circle in any order you like. Now pick 3 consecutive integers and add them. Do this for all 10 possible triples of consecutive integers and look at their sums. You will notice that at least one of them adds up to 18 or more. For example, in this particular case, this triple adds up to 21. There could be more than one triple that adds up to at least 18, but there will always be at least one. Keep in mind that not all triples will add up to 18 or more. This is true for any arrangement of integers you start with. That means no matter how you arrange the integers around the circle, you will always be able to find 3 consecutive integers whose sum is at least 18. The challenge for us is to prove this fact. Where should we start? One exhaustive way to prove this is to look at all 9 factorial possibilities and verify each case manually. But this is not the way mathematics works. Let's introduce a simple yet powerful concept that will help us solve this problem.
Suppose you have n real numbers, x1, x2, all the way up to xn. Let x bar represent their average. Now, here's an interesting fact. No matter what these numbers are, there must be at least one number, say xp, that is less than or equal to the average, x bar. Likewise, there must be at least one number, say xq, that is greater than or equal to x bar. At first, the statement may seem obvious, but how do we prove it?
The proof is surprisingly simple. Let's prove that there must be a number xq that is greater than or equal to the average x bar. Suppose, for the sake of contradiction, that no such number exists. Then every number must be strictly less than x bar. If we add all these numbers together, their sum must be less than n times x bar. Dividing by n, we find that their average is strictly less than x bar. But x bar is the average of these numbers. That's a contradiction. Therefore, our assumption must be false. So there must be at least one number, xq, that is greater than or equal to x bar. The proof of the other statement is completely similar. Back to our original problem. We just need a clever idea so that we can use the technique we just saw. For that, I am partitioning the integers on the circle into groups of 3 and leaving the number 1, like this. Why, you may ask? Just bear with me. I promise that by the end of the video, you will have the answer to this question. Now, let's call the sums of the integers in these groups s1, s2, and s3. What is the average of these 3 numbers? Clearly, their total is the same as the sum of all the numbers from 2 to 10, as we left 1 from these 3 groups. So their sum is 54, and their average is 18. This average of 18 might click something in your brain. We can apply the argument we just saw. Since the average is 18, at least one of these sums is 18 or more. And because each SI is the sum of 3 consecutive integers around the circle, we have proved the existence of such a triple, irrespective of the initial arrangement. This is exactly what we wanted to prove. Now, you might be wondering, we illustrated the argument using this particular arrangement. But the proof never depended on where the numbers were placed. For any arrangement, we can form the same 3 groups of consecutive integers. Their sums will always add up to 54, so their average is always 18. Therefore, the same argument applies, and there must always be a group whose sum is at least 18. We can explore a little more. We isolated 1 and divided the remaining 9 integers into 3 groups. What if we isolate some other number? Let's isolate 2 and repeat the same argument. This time, we get an average of approximately 17.67. Now we can conclude that at least one of the SIs is 17.67 or more. But since each SI is the sum of 3 integers, it must be an integer, and so it would be at least 18. And we reach to the same conclusion. so isolating 2 does not make much difference. If we isolate 3, then the average is approximately 17.33, and we can draw the same conclusion using the same argument. But the game changes if we isolate 4. Yes, you guessed it correctly. Now the average is 17, and we can conclude only that there are 3 consecutive integers whose sum is at least 17. Well, this result is not wrong either. We have simply proved a weaker statement about the situation. So, isolating a larger number gives us weaker and weaker results about the existence for minimal sum of 3 consecutive integers, because the average decreases. But a lower average may still allow us to conclude something interesting. Remember that there also exists a number that is less than or equal to the average. So if we isolate 1, we may conclude that there exist 3 consecutive integers around the circle whose sum is at most 18. But if we isolate 4, then we can conclude that there must be 3 consecutive integers whose sum is at most 17, and this is a stronger result. Of course, the next idea that comes to mind is to reduce this average even further to get a better bound. So the obvious choice for isolation is 10. Then we get 15 as the average, and so we can conclude that there must be 3 consecutive integers whose sum is at most 15. As a final thought, I want to draw your attention to the fact that the original question asked us to prove only one thing. But playing with the idea we use to solve the problem can be very fruitful and can lead us to conclusions that go beyond the original problem. Also, I hope it now feels natural why we isolated 1 in the first place. Most textbooks and reference books do not discuss this kind of thinking behind a solution, but it is often more important for learning than the solution itself. See you for now, and we'll meet again in the next video.